So good morning, class. Please, if you can hear me, can you note that on the chat? If you can hear me, say I can hear you on the chat. Go to the chat box. Let me know if you can hear me. Okay, thank you so much. So good morning, everybody, and welcome to today's class. A recap of what we did the last class. In our last class, we tried to show that the change in enthalpy of any reaction, when we talk about enthalpy, we're actually looking at heat of reaction. We actually step or in series of steps. So the last class, we looked at where we have to multiply a series by a factor. We also looked at where we need to divide in order to get the desired product. Like I told us in the last class, you will always have the reaction that takes place in one direction, which is your desired reaction. Now we have another concept check here. Let us verify if a reaction goes via one step or several steps, if we are going to have the same change in enthalpy. For this particular reaction, this is a one-step reaction. Sulfur 4 oxide plus half mole of oxygen to give us sulfur 6 oxide. This one represents the desired reaction and a one-step reaction. Now, the question here is for us to calculate the change in enthalpy. But we have been given the series of steps that this reaction can follow. Now, and those ones we have the enthalpy of each of the series. What do we do here? Like I told us the last class, get your clue from the desired reaction. If you look at the desired reaction, the sulfur 4 oxide is on the reactant side, that is the left-hand side. Now, if you look at these two series, series 1 and series 2, there is none of these two series that has SO2 in the reactant side or the left-hand side. But we have series 1 having SO2 in the in the product side or the right-hand side. So the first thing that you're going to do is to do what? To turn the first reaction around. What do I mean by turning your first reaction around? Now you're going to turn SO2 to the reactant side, to the reactant side, that is your left-hand side, and sulfur plus oxygen to the right-hand side. So can we quickly do that in the chat box? Turn the first reaction, the first series of the reaction, turn it around. Take SO2 to the right, to the left-hand side, that is the reactant side, and sulfur and oxygen to the product side. Forget about the sign, the arrow sign. I will understand what you're writing. If you don't know how to get the arrow sign, don't worry yourself. And remember, once you do that, the sign of the change in enthalpy will automatically change because you've reversed you've turned around the reaction. So you're going to turn again the sign of the enthalpy, which is now, it is negative here, is going to be plus 297. So quickly do that. I'm waiting. We don't have time. We need to go faster today. Can someone just do what I asked you to do so that I will know that at least someone is following me? Turn the first series of the reaction, that is this one, sulfur plus oxygen, to give us sulfur 4 oxide. Take sulfur 4 oxide to the left-hand side and sulfur plus oxygen to the right-hand side, and change the sign of the enthalpy. change the sign on the enthalpy. It's going to be positive now instead of negative. Good, but Yusuf, put good, the positive sign is there, correct. I understand what you guys are writing. Just write it anyhow, I will understand. Good. So we now have SO2 going to sulfur plus oxygen, and the change in heat is now positive. Correct. Correct. You guys are doing well. Now, let's go to the second series now. Let's go to the second series of the equation. Here we have 2 moles of sulfur reacting with 3 moles of oxygen to give us 2 moles of sulfur 6 oxide. And the change in enthalpy, change in enthalpy is minus 792 kilojoules. Again, let us go back to the desired reaction. If you look at the desired reaction, what we have in the desired reaction here is 1 mole of sulfur 6 oxide and not 2 moles. But here we have 2 moles, and there is no other place we have SO3. So it's not as if maybe when we do our addition, we will get 1 mole of SO3. We just have our SO3 in this second series of reaction. So what do we do? For this second step, we are going to divide everything by 2. Divide everything by 2. Even whatever you're doing to the reactants and products, you're equally doing to the change. To change in enthalpy for that particular step. So you're going to divide everything by 2, even the change in enthalpy. So can we do that? And let me get the answer. Go to the chat box, divide everything by 2. So it's going to be, 2 moles of sulfur divided by 2 plus 3 moles of oxygen divided by 2 to give us 2 moles of sulfur 4 oxide divided by 2, and the change, the enthalpy change, which is minus 792 divided by 2. Quickly give me the answer. Let's look at what we have on the chat box. Sorry. I just need the answer. Correct. Yusuf, I have your answer. It is correct. I need more answers before I go. What's happening? Correct. Good. Good. No, you're dividing somebody. You're dividing both things. Can we all mute ourselves? Godwin, please, can you mute yourself? Thank you so much. Back to the chat box. I need more of these answers. I need more of the answers. I need more of the answers. Correct. So let's go on. At least I have about 7 people. Okay, more than that, with the correct answer. Now that we have done that, so what do we now have? Remember, I told you in my class, you must have your pen, you must have your writing materials. So we have, what we have now is what? We have SO2 going to sulfur plus oxygen, and the change in enthalpy now is plus 297 for the first series. Now for the second series, now what we have is sulfur plus 3/2 oxygen to give us SO3. Do we have that? Now, and this is going to give us, the enthalpy change is minus 3, what did you get? 396, good. 396 kilojoules, correct. Now, remember what the next thing that we're going to do now is we'll look at what we have on the left-hand side and what we have on the right-hand side. So we are going to add. And remember, when you are adding, because they are, on opposite sides, they are going to cancel out. What do we do now? We are going to cancel out sulfur that is on the left-hand side, and the one on the left-hand side will cancel the one on the right-hand side. Now we have oxygen on the right-hand side for the first equation, and we have 3/2 moles of oxygen on the left-hand side of the second series. Now, what this means is this. It's going to be 3/2. Remember, what we are doing is minus 1 of oxygen, because that oxygen in the first series of equation is 1 mole. So it's going to be 3/2 minus 1. 3/2 minus 1 will give us what? Let's just do it like an elementary school children. LCM is 2. 2 into 2, 1. So you have 3 minus 2. 3 minus 2 is half. So what you have left is half oxygen. Are we together? So we don't have any other thing to cancel out. Can we now add up everything on the left-hand side together? Everything on the left-hand side automatically becomes SO2 plus half oxygen to give us SO3. So can we confirm that with the desired equation? Let's go to the desired equation. This is the desired equation, so we are correct. SO2 plus half oxygen to give us SO3. Now, what is the enthalpy change? Quickly give me the answer. I'm going to the chat box. Can I have the answer? Minus 99 kilojoules. More answer? Correct. Correct. Minus 99 kilojoules. And experimentally, the enthalpy change for this particular reaction is minus 99 kilojoules. So whether this reaction goes back one step or it takes place in series of steps, the enthalpy change is going to be the same. Now let's quickly go to what we have for today. And I'm going to be rushing the class now because I think that people have you already have the understanding of what the class is all about. So all the examples that we've been giving support the Hess law, which says that when a reactant is converted to a product, the change in enthalpy is the same, irrespective of the reaction taking place in one step or in series of steps. So this is a statement by Hess, and it is put at Hess law. So we've been able to support that with different examples. Now, Born-Haber cycle uses Hess law to calculate lattice energy of ionic solid. So today we want to look at the Hess law and Born-Haber cycle, and also the relationship between change in internal energy and change in enthalpy. If time permits us, we'll go on to look at entropy and second law of thermodynamics. But let's start with the Hess law. Like we said that for Hess law, irrespective of the reaction, irrespective of the path the reaction takes place, whether it takes place through one step or series of steps, the change in enthalpy still remains the same. So I have given here some examples and the solutions are there. So all you need to do is, by the end of today, I'm going to send you this slide because you will have a test on Wednesday. The test on Wednesday will comprise of all the lectures you have heard so far in CHM 121. Your chemical bonding, the kinetic theory of ideal gas, the law gases and the gas laws and equation, solutions, and chemical thermodynamics. So since CHM 121 started this semester, all that have been taught, you're going to have the test on them. On Wednesday. So just read what you have had so far. I didn't say you should go and read everything in your syllabus. No. The true physical chemistry, because even the first part of your lecture is physical chemistry. So that is what the test will be based on. So by the end of today, you will be getting the slides, my own part of the slides so far. So you have several examples of Hess here, Hess law application. Hess law here. The calculations are here and the answers are here too. So even everything step-by-step calculation. So you don't need to worry yourself. That's why I'm going to skip them in the class, and let's go to what we have today. Like I said, the application of Hess law to ionic solids is what is referred to as Born-Haber cycle. Now, this Born-Haber cycle enables us to understand the overall reaction processes through a series of steps. And like I said, it is mainly used to calculate lattice energy. It also involves other steps such as ionization energy, electron affinity. Oh, sorry. So you have the application of Hess law to ionic solids here. And you know that ionic solids is ionic compounds that are contained in ionic solids. And when we talk about ionic solids, we are talking about the coming together of a cation and an anion to form a solid compound. So what we want to look at is to calculate the lattice energy, that is the energy released when a cation and an anion comes together to form a solid product. Now, like I said, the Born-Haber cycle is used to calculate lattice energy, but it does not only involve this particular energy, it also involves the ionization energy, electron affinity, dissociation energy, sublimation energy, and heat of formation. But before we go on to how the application of Hess law using Born-Haber cycle, let us look at what a lattice energy is. Like I said, the release of energy on forming the solid. That is, when a cation and an anion combines together, a solid product is formed. And that solid product being formed, there is a release of energy. And that energy is referred to as lattice energy. How do we use all this in calculation? I don't want us to go into the definition of ionization energy, dissociation energy, and all of that. That is already defined in the slide that I'm going to give you. Let us look at what Born-Haber cycle is and look at a typical example on how you can use Born-Haber cycle to calculate lattice energy. Now, by definition, Born-Haber cycle is a cycle of enthalpy change of process that leads to the formation of a solid crystalline ionic compound. I want us to take note of some things here. I want us to take note of some things here. Formation of a solid crystalline ionic compound from the elemental atoms. Please underline the elemental atoms. From the elemental atoms in their standard state, and of the enthalpy of formation of the solid compound, such that the net enthalpy becomes zero. Do not bother yourself about this grammar. I am going to explain it in a very simple way. Now, let us consider the Born-Haber cycle of sodium chloride. With that, we are going to understand what this statement means. Now, for the formation of sodium chloride, first of all, the heat of formation of sodium chloride from sodium metal and chlorine gas can be measured experimentally. What this means is this: the heat of formation here, that is sodium, solid sodium combining with the chlorine gas, will give you your solid sodium chloride. And the heat of formation is minus 411 kilojoule per mole. Now, the formation of solid sodium chloride from sodium metal and gaseous chlorine is not a one-step process like it is assumed here in this heat of formation. It is not a one-step process. It involves different steps, or what we refer to as series of steps. Now, and because it involves series of steps, each step will have its own heat change. And so we need to do what? To look at all of these heat changes for all the processes. Now, all these other excuse me, sorry. All these other steps, sorry. All these other steps will have its heat change, and this can be measured experimentally. What do I mean by that? Let's go back. Remember, we said in calculation of that we use Born-Haber's circle to estimate the lattice energy. So it is by indirect calculation. But that Born-Haber cycle also involves other processes such as ionization energy, electron affinity. All these other steps, series or processes can be measured experimentally, except your lattice energy. Your lattice energy cannot be measured experimentally, but your ionization energy can be measured experimentally. Remember, we said we can use calorimeter to measure the heat change. Now, electron affinity can be measured experimentally, dissociation energy can be measured experimentally, and so on and so forth. The only thing that cannot be measured experimentally is your lattice energy. That one can be obtained by an indirect calculation. Now, what do I mean by that? So let's go to a typical example again, the one we were looking at of sodium what? Sodium, the formation of sodium chloride. The formation of sodium chloride will give us, that is a one-step formation is this. That is why you have heat of formation as minus 411 kilojoule per mole. But like I said, this process involves series of steps. It is not as we have written it here, a one-step reaction. No, it involves series of steps. And what are those steps? Now, the first step is that the solid sodium atom sublimes to gaseous atom by absorbing heat energy. And this heat energy is referred to as heat of sublimation. Now, what does that mean? This is the first thing that happens. The solid sodium sublimes to gaseous sodium, and there is a heat energy or a heat change. And that is referred to as heat of sublimation. This heat of sublimation is not experimentally to be plus 107 kilojoule per mole. Now, once this happens, this gaseous sodium will absorb ionization energy. Sorry, it will absorb ionization energy to release one electron and becomes positively charged. And the heat energy here is referred to as heat of ionization energy. And that is, this also will be measured experimental. That is, your meter, your colorimeter will give you this. And this is plus 502 kilojoule per mole. Now you have two reactants, the sodium metal and the gaseous chlorine. Now, the top step here is that the diatomic gaseous chlorine will break into two individual chlorine atoms by absorbing a bond energy. So it will absorb bond energy to break into two chlorine atoms. So what this means is that if you have the bond energy as 242, because you have two atoms being formed, you're going to divide this by 2 so that each chlorine atom will have plus 121 kilojoule per here. Now, what is happening in the fourth step? The first step is that the chlorine atom will accept an electron. It will accept an electron to become negatively charged. And in that, the energy that this particular energy is equivalent to electron affinity. And that is minus 355 kilojoule per mole. Now, you already have your cation here, and you have your anion as step 4. Now, there's going to be is network. The volume is low. Yeah. I guess it's network. Can you hear? Okay, so sorry about that. I have to restart again. Let me see if it's going to be better. I have to restart the class again. I have to restart again, but I need to get Dr. Agumbiade to make me a co-host, so I'll be able to share the screen again. So I want to call him now, and I'll get back to you. So sorry. I can still continue with the class while we wait for him. Please, can you make me the co-host? The team went off. I have to log it back. Okay. So sorry about that break in transition. I think the audio is better now. What's happening now? I want to share the slide. Okay, we are here. So, a lot of things here. Okay, this is where we are. So I'm saying that now we have the cation and we have the anion coming together to form our solid sodium chloride. So this is the solid sodium chloride. And when the ionic solid is being formed, there is a release of energy equivalent to lattice energy. But because lattice energy cannot be measured experimentally, we need to calculate it. That is why this has a question mark here. Now, the formula that we have here is that your heat of formation, which is the energy of this one-step reaction, is equal to the heat change of all the other processes from number 1 to number 5, including your lattice energy. So what we are saying is that heat of formation is equal to heat of sublimation plus heat of ionization plus heat of dissociation. The reason why we put that here is because here in our heat of dissociation, we have two atoms of chlorine. So you are going to, because we are using one atom here, you're going to divide it by 2. But if it's a case where it is one atom, you don't need to put half. So half depends on what you have and what is happening here. Plus, this is the electron affinity plus your lattice energy. So if you add up all of these things, you're going to have that the lattice energy is, I think, minus 788 kilojoules. So that is how to calculate, to use Born-Haber cycle to estimate the lattice energy of an ionic compound. Remember, this is only for ionic compounds. You can only use that Born-Haber cycle to calculate lattice energy from ionic compounds. I still have another example here, which I want you to look at later. So you have all of these things. Just, excuse me, just put in all these values and you will get this. So you can look at that later because of the time. We need to hurry. Now I have another example here. The one for lithium chloride, formation of lithium chloride. So what I want you to do is to just follow this example that we have in class. The explanation, I've explained it in class. Just follow that explanation and look at what is happening in the Born-Haber's calculation of lattice energy for lithium chloride. It's still the same thing. First of all, you have your sublimation or heat of atomization is still the same thing. The solid lithium is going to get short lithium and so on and so forth. So you calculate the lattice energy and you get your answer. It's as simple as that. Now, the next thing that I say we are going to look at is the relationship between change in internal energy and change in enthalpy. I'm going to just give us the simplest and the best way to understand this. We have a system. That system will contain some amount of energy in it. By just being a system, it will have some amount of energy in it. This amount of energy that is stored in any system is referred to as internal energy. The energy that is stored in a system is referred to as its internal energy. Now, this energy that is stored in a system, some of this energy is available for work or conversion to heat, depending on what. Conversion to heat is also work. The energy stored in a system that is available for work is called the enthalpy of the system. So that is the difference. You can have energy stored in a system. If that energy is not available for work, it is internal energy. But the available energy for work is referred to as enthalpy of the system. So for example, now, you have a system that has a stored energy of maybe 50 kilojoule per mole. And this system can use 2 kilojoule per mole to do work. That 2 kilojoule per mole is referred to as the enthalpy of that system because it's only that particular one that is available to do work. So that is the relationship. That's the difference between change in internal energy and enthalpy. Now, what's the relationship between these two? The relationship between these two is that the change in the enthalpy of the system is equal to change in its internal energy plus change in the product of the pressure times the volume of the system. Product of pressure times volume of system is actually work done on the system. So like we say, it's just the work. So you have enthalpy change. Enthalpy change is equal to change in internal energy plus work done on the system. That is the relationship between the two of them. But the difference between the two of them is that internal energy is the energy that is stored in a system at a particular time, while change in enthalpy is that particular energy that is available for work. And again, change in enthalpy is considered as a constant pressure, while internal energy is the heat released or absorbed at constant volume. So these are the two different things, but the relationship is that an enthalpy change is equal to change in internal energy plus work done on the surroundings. Now, this is a way to express enthalpy change. The enthalpy change of going from a reactant to a product. If we are considering a reaction, now all of these things here is what you will understand. But instead of you to listen to the class, you're asking if you will get your slide. You get slides after the class. Personally, I don't like giving students slides, but let's just go. So you have the internal energy and the volume of the reactants. You also have the internal energy for the product, and you also have the volume of the product. So adding up everything, because you know that when you go from your reactant to your product, when you're adding up when you're calculating the change in enthalpy, it's going to be enthalpy of the product minus enthalpy of the reactant. And remember that the enthalpy of the product involves the internal energy and the volume of the reactant at constant pressure. That's why you're seeing this P. The P here shows that it's at constant what? Pressure. So in all, what we are saying is this, that change in enthalpy is equals to change in internal energy, because this change involves both the reactant and that of the product. That is the internal energy of the product minus the internal energy of the reactant will give you change in internal energy, plus the pressure, which is a constant, times change in volume, which is the volume of the product minus the volume of the reactant. Then another relationship that we want to look at is when you consider a chemical reaction that is taking place at constant temperature. We've already noted that of constant pressure. At constant temperature, we are going to be involving the number of moles of the gaseous reactants and products. And so you have delta Ng. That is, Ng is just representing the number of moles of the gaseous products minus that is change in the number of moles of the gaseous products and the reactants. That is why we introduce this. Now, because the reaction is taking place at a constant temperature, so we are going to look at the gas and what's the temperature. So that is what is involved here when you're looking at that. So for these two equations, you have change in enthalpy to give you change in internal energy plus pressure times change in volume. This is the formula or the enthalpy change when the reaction is taking place at a constant pressure. When the reaction is taking place at a constant temperature, the change in enthalpy is going to be given as change in internal energy plus change in the number of moles of gaseous moles, number of moles of the gaseous substances, times your R and T, which is your other gas and all of that. Now, when you have this, what we are looking at now is, let us now give a summary of all the conditions for this to take place. If this happens, the delta H, that is the change in enthalpy, will be equal to your change in internal energy when the reaction does not involve any gaseous component. So if the reaction does not involve any gas as 0. So automatically, if that is 0, 0 times RT is going to be 0. So you have delta H is going to be pressure times 0, which is 0. So these are the possible conditions for enthalpy change to be equal to change in internal energy. Now, for you to have for the change in enthalpy to be different from change in internal energy, these are some other conditions. So you get that. I mean, you see this when you get the slide. Okay, we can quickly run over that. We still have, I think, 18 minutes. So the first is when there is an increase in the number of moles of gaseous components, which means that if you have, okay, let's look at what we have here. Here you have 1 mole of the reactant giving us, this is the reactant giving us these products. Now, this reactant is 1 mole. Now, the product, you have 1 of PCl3 and 1 of Cl2. So you have 1 plus 1, 2. So the number of moles for this product is 2. And the number of moles for the product, that is the moles of reactant, is 1. So change in the number of moles of the gaseous substance will be 2 minus 1. So you're going to have 1. So you don't have 0 here. You have 1. So there's going to be an increase in the change in enthalpy. So change in enthalpy is going to be greater than change in internal energy. Again, you have another one here. You have 1 mole of the reactant and producing 1 mole of the product. So here you have no, this is this should be 1, 2. We'll look at this other one later. Let's go to the next slide. There is also possibility of a change, of a difference in the enthalpy change and the internal energy when there is a decrease in the number of moles of the gaseous components. When there is a decrease in this and you have that the enthalpy and the change in enthalpy is less than change in the internal energy, is such that the moles of the reactants, the moles of the gaseous components of the reactants is greater than the moles of the gaseous components of the product. So here you have 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas to give us 2 moles of ammonia. Ammonia is the product. So you have 2 minus 4 because this is 3 plus 1 to give us 4. And 2 minus 4 is a negative sign. And it will give us minus 2. So because you have a negative change in number of gaseous components, the change in enthalpy is going to be less than change in internal energy. So in summary, we have that for gaseous reactants, the difference between your change in enthalpy and the internal energy depends on change in the moles of the gaseous components. Now, if the change in the moles of the gaseous components is equal to 0, the change in enthalpy is going to be equal to change in internal energy. If it is positive, the change in enthalpy is going to be greater than change in internal energy. And if the number of moles of the gaseous component is negative, the change in enthalpy is going to be less than change in internal energy. Please, these 3 description is very important. That is what is summarizing the relationship between your enthalpy and change in internal energy and the conditions in which these occur. So it is very important, these 3 description here. I don't want to call them equations so that you don't, they are processes. Now, a summary of the difference between enthalpy and internal energy, which I have said earlier, that you have internal energy when you have the amount of energy that is stored in a system, you call it internal energy. The energy that is available for work is what is referred to as the enthalpy of the system. And the enthalpy change of a system is at constant pressure, while the internal energy change of a system is at constant volume. So these are the basic difference between your enthalpy and the internal energy. We also looked at the relationship between the 2. Now, the next thing we want to look at yes, 1 minus 3 over 2, you're correct. The second equation is meant to be 1 minus 3 over 2. You're correct. So 1 minus 3 over 2 is going to give us minus, I think it's going to be minus half. So let's look at that in the next class. I'm rushing to complete this. So the next thing we want to look at is entropy and second law of thermodynamics. I think this is going to be the last aspect of my lecture with you. We'll be looking at entropy and second law of thermodynamics, free energy change and changes due to melting and boiling. We are not going to complete this, but wherever we get today, on Wednesday, we just use like 10 to 15 minutes to wrap up the class while we start our test immediately. Please, there's going to be a test on Wednesday. There's going to be a test on Wednesday. So when we say the second law of thermodynamics, now listen to me. I'm going to explain this as simple as I can. Now, the second law of thermodynamics is a fundamental law of nature. If you look at what you have in this picture, you see that water is running down. That is, you have water running down the water floor. The waterfall. Now, this particular reaction occurs spontaneously, which means it's a natural thing, it's a natural process, it's a natural phenomenon. That is why I say that the second law of thermodynamics is a fundamental law of nature. Water can never run up the water flow. You cannot have water running up the opposite direction without an external aid. You can only have this water pumped somewhere and you raise maybe you're using a hose. That is when there is going to be a reverse of this. And that is not natural because you have actually, you're using an external aid. You have actually added energy to it. But naturally, water can only flow through this direction. Now, one of the uses of second law of thermodynamics is to determine whether a process is spontaneous or not. When you say that a process is spontaneous, it is a process that can happen on its own without any external aid, without you helping it or putting in energy to make that thing to happen. It happens spontaneously. Let's look at another example here. The arrow of time. The arrow of time. You know that there is no how you have the time going from your right to your left. Look at your wristwatch. Your wristwatch, time always goes from where? It goes from left to right. So even if you want to turn it, it's going to involve an external aid. Maybe you need to remove something and turn the wristwatch and do whatever. But naturally, this is how time moves. It moves from left to what? To right, and never from right to left. So though these are spontaneous processes, it's the process that occurs naturally without any external aid. Now again, we'll look at another example, an ice cube. An ice cube. Once you get your ice, over time, it will start melting to a liquid. Without you adding anything to it, it will just on its own naturally melt over time to a liquid. So that is a spontaneous what? The spontaneous process. Now, we also understand that heat flows from hot object to cold object. It's a natural thing. Naturally, heat flows from a hot object to a cold object. If you want the reverse to happen, that means that you're going to have an external aid. Heat does not naturally flow from cold to hot, except if an energy is being added. That is, you need an external aid. For example, now, what we have in our refrigerator, when you put a hot thing in the refrigerator, it gets cold. Whatever hot thing you put in the refrigerator cannot go back to make your refrigerator to be what? To be hot. But remember that it is not a natural process. There is an energy that is cooling that is doing that, such that it's only when the refrigerator is working that will happen. So it's an external aid. It is being aided. Now, another example that I have here is this picture here. This picture here is showing us that this is a clean room. This room has been arranged. It is in order. Now, even if you did not mess up this room by yourself, over time, things in this room will start wearing out. They will start changing color. You know, the rooms will get old. The house will wear. The things here will start getting rough and all of that. So it will be going from a state of order to a state of disorderliness. So a clean room is not will go to a disorderly room or a disorderly condition spontaneously. You don't need to edit. You don't need to add anything. If you leave this room here, if you come back in the next 5 to 10 years, you will see that everything here will change. Everything here, you will see the room will become rough. Even when you did not, you are not the one that add the dirt or mess it up. It will automatically, naturally go to a dirty room or a room that is not organized. But for you to get this rough, this disordered room to an ordered room, you need to add effort and energy. You need to start packing all these clothes, clean up of all these things. This is energy. You're adding effort. You're using energy to do all of these things. So going from a disordered room to an ordered room, it is not a spontaneous process. It requires energy input. So what we are saying in effect is that we are saying that we've already said that the second law of thermodynamics is a fundamental law of nature, and you use it to determine whether a process is spontaneous or not. There is this particular term that actually define or describe the second law of thermodynamics, and that is entropy. When we talk about entropy, we are talking about the degree of disorderliness. The degree of disorderliness of a system. We have it here, the quantitative measure of disorder. Entropy describes the degree of disorderliness of a system. And that is a term that is used best to describe to describe second law of thermodynamics. Now, the second law of thermodynamics says we'll just summarize it, that it says that natural process, that the change in entropy is greater than zero. So for every natural process, the change in disorderliness is greater than zero, which means that you know that anything that is greater than zero is on the increase. So that for every natural process tends to go toward the state of disorderliness. We have explained that using all of these pictures that we have here. So that is what describes the second law of thermodynamics. Again, we can say that all processes that occur without external aid, that occur spontaneously, will obey the second law of thermodynamics, and they will tend to go towards the state of disorder. That is, the entropy of the system will increase. Now, for this particular second law, what we are looking at is that what we can say in another way is that for all irreversible processes, that the change in entropy is greater than zero, meaning that the degree of disorderliness increases. Another example is to look at that we have here is the perfume we use. When you spray the perfume in a room, once you spray it on your clothes, it's on your clothes that you spray, but because even if you don't spray it and you open the bottle, the odor will spread throughout the room. And it is impossible for you, without an external aid, to bring back the perfume, that the molecules of perfume that has evaporated from the bottle back into the bottle. It is not possible. Another spontaneous system is miscible liquids left together to mix. For example, if I have an ethanol and water and I leave them close to each other, over time, two of them will mix. I cannot separate the two of them without an external aid, without energy input. I can only do that if I go on to use a distillation setup. Then I will be able to separate them fractional distillation based on their boiling point. Ethanol will come, then water will come. But without the external aid, without the energy input, I will not be able to do what? To separate the two miscible liquids. And so, for all irreversible processes, we say that the change in entropy is greater than 0. Is your time up? Okay, I still have 3 minutes. The change in entropy is greater than 0. Now, that is for entropy of an isolated system. That is all that we've been saying now, because you know that, for example, we are human beings, we are a closed system. So we can always, we can't say that our system is spontaneous. No. So we are looking at entropy of an isolated system, that the entropy change is greater than 0. Is greater than or equal to 0. It cannot be less than 0, because if it is less than 0, it is now going towards orderliness. But remember that for a natural process goes from order to disorderliness. So that is what we have here. So in summary, we are saying that for all reversible changes, that the entropy change is greater than 0. And for all other processes, that the total change of the entropy is greater than or equal to 0. So let this be our take for today. And on Wednesday, we are just going to conclude looking at the Gibbs free energy, and how to calculate the melting and the boiling of system. So that is what we will do on Wednesday before the test. Please, you need to tell your colleagues or your classmates about the test on Wednesday. It's going to be an online test, so the link will be sent to you in due time. But for now, you'll get the slides. Don't worry. I'll look for a way to get the slides across to you. Probably today or before the next class. We have a class on Monday. Then we now have Wednesday. If we're able to finish our class on Monday, that would be very nice, so that we know that on Wednesday we're just coming to just summarize and then have our test. So please, the topics for the test is what you have done since this semester on CHM 121. I think I am about the 6th lecturer that I've taught you. So you've done, I think, chemical bonding, kinetic theory of ideal gas laws and equation, solution. You also did thermodynamics, which is still part of what I am taking. So that is just what the test will comprise of. Anything that we did not teach you, you will not see it in the test. It is what we have taught so far. That is what the test will comprise of. So please, make your questions available. Probably on Monday, I'll have time to take some questions, so that we'll just wrap it up and you get ready for your test on Wednesday. Thank you so much and have a good day. Good. Enjoy your weekend. Thank you. Bye. Yeah, it's going to be a multiple choice question, and it's going to be online. Thank you so much. Thank you for saying that it's understandable. God bless you. Thank you. But you can show me that in the scores of your test. It's not that it's understandable, and when I give you test, you now mess me up. I don't want that. Anybody that messes me up, I'll come to class and call your name. That's my style. Now on Monday, good. Please listen. On Monday, I'm going to be giving us questions. A lot of questions in class. And please, on Monday, I want everybody to sign in with your name, and you sign in with your name, because if you answer my question, there's going to be a small gift, very special small gift for you. I'll tell you where to come and collect it, probably in my office. So get ready for me on Monday. I'm just going to ask you questions based on what I've taught you. I started the class with you last week. So I'm going to concentrate on my own aspect. So don't bother yourself, but please, throughout this weekend, try and go and get yourself ready for the test. You know, you have CHM 121 is the course is not I mean the syllabus is I wouldn't say it's too many because you students you can always quote lecturers, but you need to start getting ready on time. That is just the summary of it. So we'll see on Monday, then on Wednesday. So you get ready for me on Monday.